This is FRQ number 2 from the Rotational Mechanics review packet. We have a solid sphere of 1.5 kilograms. That's the mass. And it's going to roll down an incline. So I'll make just kind of a brief sketch over here. It's rolling without slipping. That should be a cue for you. We know the angle theta is 35 degrees. We can use some trig to figure out the height. And that's something we'll definitely need to do. We'll multiply the sine of 35 times 7. And the reason that we know that is that the hypotenuse, which is the length of the incline, is 7 meters long. We assume that it starts from rest and the moment of inertia is given by 2/5 mr squared. This is a conservation of mechanical energy problem. We can say that the energy at the top, which is going to be all gravitational potential energy, is going to be equal to the sum of mechanical energies at the bottom. And if we call the bottom of the incline here, if we call that kind of dashed line, if we call that 0, then it has no gravitational potential energy when it gets to the bottom. It only has kinetic energy, but it also, because it's rolling without slipping, has rotational kinetic energy. That's kind of this new variable that shows up in Unit 5 concepts. So I can replace all of these. This becomes mgh. The kinetic energy, also given to us on our equation sheet, is 1/2 mv squared. And the rotational kinetic energy is 1/2 I omega squared. Now, there's a bunch of key substitutions that I need to make here. I need to substitute in something for I. That's right here. That's what's going to get substituted in for I. They give it to us, 2/5 mr squared. And omega is the weird one, right? So v tan, or the tangential speed, is equal to omega r, and therefore I could solve that for omega, and I get v over r is equal to omega. And therefore omega squared is v squared over r squared. Now I'm going to make all these substitutions. Let's go ahead and do that. So this next line, I get mgh. On the right-hand side, I get 1/2 mv squared plus 1/2. Now I have to substitute in for I, so that's going to be in these brackets. It's going to be 2/5 mr squared. Again, that's given to me. I don't need to memorize formulas for moments of inertia. And then I need to make the substitution in for omega squared. It's v squared over r squared. So now there's going to be a whole bunch of things that drop out of this. The first one is mass. There's a mass variable in every term. That's very convenient. The r squared over here in the rotational kinetic energy terms basically cancel out, right? I have one in the numerator and one in the denominator. And so now I'm ready to kind of continue. On the left-hand side, I have gh. And then to the right of the equal sign, I have 1/2 v squared. And now I need to multiply the 1/2 and the 2/5 through. That's 2/10. And the only thing that's left is the v squared. So now I have to add 1/2 and 2/10. I'm going to have to find a common denominator. It looks like it's going to be 10, right? So that's going to be 5/10 v squared. And I'm going to add to it 2/10 v squared. And when I do that, I'm going to get 7/10 v squared. So in this problem, I'm calculating the linear speed at the bottom. Really, v, right? V tan. So I get gh is equal to 7/10 v squared. And so in this final expression, I'll just multiply both sides by 10 over 7. And so I get 10 divided by 7 times gh is equal to v squared. And so I'll take the square root of both sides. So I get root 10/7 gh is equal to v. Now, they didn't give me the height h, but they did give me the angle and the length of the incline or the hypotenuse. So I could replace h if I wanted to. Let's kind of write this one last time. I know I'm going into kind of some extra space underneath, but this hasn't changed. It's still 10/7. G is just the number 9.8 because we're on Earth. And H is going to be the sine of 35 times the length of the incline, which is 17. And when I do that, I'm going to write this out as 7 times the sine of 35 degrees. And that's equal to V. So when I multiply all these things by each other, I get my final answer of 7.5 meters per second when the ball gets to the bottom. That's going to be a slower number than if I had ignored rotational kinetic energy altogether. If this was sliding without friction instead of rolling without slipping, then there would be no energy conversion into rotational kinetic energy, and my linear speed would be higher. The question then now is, what is the angular speed of the sphere at the bottom of the incline? This requires me to apply V tan is equal to omega r. And that's what they're asking me for, the angular speed, which is omega. So that's just going to be V tan, which I've solved for in part A, divided by the radius of the sphere is equal to omega. And when I plug these numbers in, that's just going to be 7.5 divided by 0.15 meters, and I get 50. And I'm going to get standard units of radians per second. Is equal to omega. Okay, so that's my answer for part B. Part C goes on to ask about the linear speed being dependent on the radius or mass of the sphere. And we can see from the expression earlier, let's go up here to this piece right here. This was my expression right near this blue check mark. I'm going to now box it in. There's no r and there's no mass. We can see right here, radius goes away, and we can see the mass goes away in every term. And so the answer to part C is no. It doesn't. It's not dependent. The linear speed is not dependent on the radius or mass of the sphere for this one. And then the question is, does the angular speed depend on the radius or mass of the sphere? And we can see that from this question right above it, V tan, which we've already said is not affected by radius or mass. So that's not affected, but the bottom is. The bottom is affected by the radius. So if it's going the same linear speed, but it's a smaller radius, it's got to be spinning faster. And so angular speed is dependent on radius, but not mass. And so you would need to write that out. And the only reason that I'm not is because the screen recorder is behaving a little poorly right now. And if you can tell, it's not writing very quickly. So those are the solutions to question number 2 on the rotational mechanics packet.